Hello and welcome to our last session of a tutorial to Mill Standard 1553. In our previous sessions we looked at the Mill Standard 1553 messages, the timing between messages, and techniques for building lists of messages. We'll now look at some of the hardware issues relating to 1553. Some issues, such as Manchester coding and differential signals, are important for anyone who may use an oscilloscope to help debug a system. Other issues, such as bus termination, are important to anyone setting up a bus, whether in the lab or on an aircraft. Please note that this is only an introduction to Mill Standard 1553. Anyone using these notes as a basis for building an aircraft is requested to notify us. We'll take the train. Manchester encoding describes how the voltages flowing over the bus should be interpreted as ones and zeros by the devices connected to the bus. Each word begins with a sync signal, which looks different than a regular data bit. Devices use the sync to identify the beginning of a word. The signal moves up and down between plus 3.75 volts to minus 3.75 volts. In the middle of each sync or bit, the voltage moves from one extreme to the other. The direction of this move determines the bit value. The voltage may also change values between bits, particularly if two bits of the same value are transmitted one after the other. Here is a diagram of the signals for a 1 bit followed by a 0 bit. At the beginning of the 1 bit, times 0 on the timeline, the voltage on the wire is plus 3.75 volts. Midway into the 1 microsecond bit, the signal plunges to minus 3.75 bits, where it remains until the end of the bit. The next bit is a 0 bit, so the signal continues at minus 3.75 volts until the middle of the bit, where it rises to plus 3.75 volts and remains there for the remainder of the bit time. Sync signals look similar, except that midpoint comes after 1.5 microseconds rather than after half a microsecond. Looking at a 1553 bus using an oscilloscope will show signals that behave pretty much as described in the previous slide. The one difference is that in the real world there are no right angles, and the transition from up to sideways is a bit more gradual. A sinusoidal wave has a very gradual curve from one value to the next, whereas a trapezoidal curve has some angles but not 90-degree angles. Even devices designed to transmit and accept trapezoidal signals will be able to properly interpret sinusoidal signals, so it is possible to use a mix of remote terminals on an aircraft as long as the bus controller transmits sinusoidal signals. The signals described above assume that a single wire is used for 1553 communications. Actually, 1553 uses what is called a twisted shielded pair of wires. One wire, let's call it bus A, looks as described. The second wire, call it A prime, is exactly the reverse. Where A is at plus 3.75 volts, A prime will be minus 3.75 volts. Where A rises at mid-bit, A prime falls at mid-bit. Confusing the two wires is not a good idea. These two wires should not be confused with dual redundancy. Dual redundant systems have a bus B comprised of wires B and B prime in addition to A and A prime. Why use differential signals? The meaning of plus 3.75 volts is 3.75 volts higher than ground. Similarly, minus 3.75 means 3.75 volts less than ground. But what is ground? Ground is a signal obtained by sticking a metal pole into the ground and connecting your system to it by wire. As you might imagine, this is inconvenient to accommodate when designing an airplane. A differential system works by comparing the two signals. If both signals are at minus 3.75 volts, they are equal. If one is at plus 3.75 and the other is at minus 3.75, they are 7.5 volts different from each other. This difference between the signals is independent of ground. In addition, if an unexpected electrical field should come up, due for example to an electrical storm or kid turning on his video game, it could affect the value of a signal relative to ground. However, since the differential signals are shielded, any effect on one will likely also affect the other. If both signals are increased by 3 volts, the difference between the signals remain the same. A 1553 network consists of the bus controller, up to 32 RTs, possibly one or more bus monitors, which are essentially completely passive RTs, bus couplers, and terminators. We'll look at a diagram of all these elements soon. Think of the bus as a long wire going from one end of the plane to the other. Periodically, a wire splits off from the main bus to attach to a BC, RT, or monitor. At either end of the bus, we put a bus terminator. This terminator fools the signal into thinking that the bus continues on forever, which prevents a phenomenon called bouncing, in which the signal bounces back from the end of the wire and causes echoes on the bus. Here is a diagram of the bus we just described. At point B, the main bus splits off to reach the BC and various terminals. Attaching stubs to the main bus is called coupling to the bus. This can be done by simply connecting the stub wires to the bus wires, which is called direct coupling, or by using an additional device called a transformer coupler. Direct coupling is a less clean method of connecting devices, and the spec restricts the length of stubs connected in this manner to 1 foot in length. Transformer coupling uses a passive device called a transformer, which contains circuitry to filter the signal. Because the signal is cleaner, the spec allows stub cables connected via transformer couplers to be up to 20 feet long. Direct coupling is never used on aircraft, but can be used in a laboratory test environment. This is a diagram of a 1553 network. The network contains a bus controller shown as a test card and a number of RTs. On the far left is bus A with terminators on the very top and bottom, and a number of couplers in the middle. Each coupler contains one or more stubs. Each stub can be used to connect to a different RT. Each device has 2 points that can connect to a bus, one for bus A and one for bus B. Each connection is made using a twisted shielded pair cable. This wraps up our session on hardware issues for the Mill Standard 1553 bus. I hope you have found it informative. If you have any questions or comments, you may find our contact information on our website at www.mill-1553.com. Thank you.